Hello everyone. I'm Alejandro Cano. I'm a PhD industrial student, and in a collaboration between UC3M and GMV. And I'm here to present you my first year of the PhD, which is about advanced methods for orbital uncertainty characterization applied to space surveillance and tracking. So I'll try to summarize to you my first year, starting with an introduction with the motivation and the concepts. Then I'll go through the main core of my methodology, and finally I'll show you some results, some ongoing work, and future work. So let us start with the problem, with the motivation. So as you all know, there is a huge problem nowadays in the space. We have the new space concepts, the mega constellations, and the space debris, and this causes the space to be overpopulated. And well, this in the end causes the safety and accessibility of the space to be jeopardized. I don't know if I have a pointer here. Oh yeah. And for these reasons, space surveillance and tracking services are applied through the institutions or companies. And basically, they provide these three main services: collision risk assessment, re-entry analysis, or fragmentation analysis, to try to mitigate this problem. Well, all of these services need an accurate knowledge of the uncertainty of your system. And, well, this leads us to the problem of uncertainty realism. This is how well characterized is the uncertainty of the system. So in this example, for instance, if Google Maps is telling you that you are here and is telling you that this is your uncertainty, if you are in fact here, you are completely lost. So a more realistic representation of your uncertainty would be this greater circle. So this is basically what I'm trying to accomplish in the space. So the goals of my thesis is first to model the uncertainty sources in dynamic models, focusing on the atmospheric effect in LEO, for instance, the atmospheric density, solar radiation pressure in GEO, or different measurements models like range biases, range rate biases, and so on. But then not only modeling the uncertainty, but also quantifying it. This is estimating the actual uncertainty that we have present in the space environment. So let us start with the core of the methodology, the initial steps. So the uncertainty under Gaussian assumptions can be represented via a covariance matrix. And this is the uncertainty representation that we typically work on in the nominal operations in the space. Typically, these covariances are obtained after the orbit determination process with nonlinear weighted batch least squares estimations. And these processes are known to lack of realism because they do not account for the dynamical model uncertainty. So basically, you generate a covariance, typically called the noise-only covariance, where only the uncertainty in the measurements of the orbit determination is taken into account, not the uncertainty in the models. This leads to a lack of realism, and this is the problem that we want to, if not solve, because that may be impossible, at least to mitigate. So, the core of our methodology is the considered parameter theory. This theory basically consists in including additional parameters into the equations, which are defined to have a null mean with a certain variance. The objective is that these uncertain parameters will gather the uncertainty of the dynamic models so that we can represent it via these parameters. Then the covariance can be corrected with these parameters and obtain the so-called considered covariance, a more realistic representation if you can achieve it. So one of the greatest advantages of this methodology is that we are able to model specific uncertainty sources. This is, we can tackle separately the atmospheric drag or the solar radiation pressure or the prediction of the solar proxy indexes. But what is the greatest problem that we have? That the variances of these parameters, you can model them as you want, but you don't know the variance of the parameters. This is the greatest problem that we have. And, well, one possibility could be to use typical or safe values, but we propose a covariance determination methodology to actually estimate those parameters. Well, how are we doing this? Well, these are our ingredients. So on the one side, we want to achieve a realistic covariance. This means that the probability distribution of the state vector must be represented by that covariance under Gaussian assumptions, for sure. Therefore, if we go to the Mahalanobis space, to the Mahalanobis distance, which is basically this equation, the distribution of this distance should follow a chi-square distribution of the corresponding degrees of freedoms in case that we are having a realistic covariance. And as we explained before, this covariance, this PC, the considered covariance, is a function of the unknown variance of the considered parameters. Therefore, we propose a methodology to estimate those variances so that a distribution of Mahanovic distances squared follows the chi-squared distribution. But in order to do this, we need a population to estimate. We need data. Where do we get it? From what we may call an operational Monte Carlo approach. This is, in nominal SSA operations, we start with some observations for an object. We are focusing on a certain object. So we have observations, and then we perform an object determination. For this example in Leo, during 7 days of observations. Then we always propagate the orbit to predict to the future. And we are, for instance, interested in analyzing what will happen at this epoch. So this Mahanovic distance. Therefore, at that epoch, we compute the state, we compute the noise-only covariance, and everything that we need to build these two values, except the variance of the considered parameter, which are still unknown. Then, as we do in nominal operations, we wait for the next day, and we receive more observations. So we repeat the process the next day, and we continue to do so until we have observations in the range of the propagation of the first orbit. And what we propose here is to use this estimated orbit as reference for the Mahanovic distance. We have called this operational reference orbit. And as you can see here, we take this covariance and this state to be used as reference. Why? Because that estimation is much more precise than your propagation. So it is precise enough to be used as reference with the proper care, of course. So this is how we build our population for the optimization. So the last step of our main methodology is, of course, the optimization, to find the variance of the parameters. So for this, we use empirical distribution function test statistics, such as the well-known Kramer von Mises or Kolmogorov-Smirnov, and a root finder algorithm, such as differential evolution, to be able to estimate multiple parameters at the same time. So basically, we start with a population of Mahanovic distances such as this, without any correction, very far from the chi-square behavior. And after finding the correct variance of the considered parameters with this procedure, we end up with this kind of final distribution, much more realistic and matching the expected theoretical behavior under causal assumptions. So this is basically the core of the methodology. Let's see some results. So, of course, we first performed a lot of simulations, and here I'm showing you a case with 3 simultaneous considered parameter estimation, in this case atmospheric aerodynamic model error, range bias error, and solar proxies prediction error. This is quite complex because when mixing different uncertainty sources, you may have coupling, you may have different issues between them, but in the end, we achieved quite good accuracy as compared to the input uncertainty in the simulations, as you can see here. But also, what you can see here is the covariance containment. This is a direct metric of covariance realism because it represents the amount of points of samples laying inside covariance ellipsoids, different covariance ellipsoids. And what we see here is that the average containment without considered covariance is really similar to the theoretical results of the corresponding multivariate distribution, multivariate Gaussian distribution, showing a really big covariance realism improvement. So this is in terms of simulations, and we are we are about to publish a paper with these results. And we also had some results with real data from Sentinel-3A, and we presented this in the European Conference on Space Debris last year. Then some quick results in GEO. We also performed this analysis for GEO estimation, and in this case focusing on the solar radiation pressure and the clock time biases, again with really good containment results and really good accuracy. And in this case, we can also focus on the differentiation between the different impact of the uncertainty source in the growth of the covariance. Because, as I said, the best part of this methodology is that we can distinguish between the corrections that we apply to the uncertainty. So we can see which correction comes from this parameter and which correction comes from another parameter. And then, now only 2 slides left, some quickly overview of the ongoing work. So we are also now moving into more complex models of the uncertainty. Here at ICSA last month, we presented an analysis with a time correlation stochastic model for the atmospheric density. We were interested in a parameter called lambda, the inverse time scale, to control the strength of the correlation. And for instance, this example that I'm showing you here is that we found that when the stochastic noise is really, really strongly correlated, that you reach almost a constant perturbation, you have the greatest covariance propagation. Whereas if you are basically in a deterministic scheme, you get the lowest covariance propagation, and it can be even comparable to the purely Gaussian in a non-dominated environment by the drug. And then what I'm presenting next week in another conference at Kepasa is that we are using this covariance correction to improve the collision avoidance, the collision risk analysis assessment. Well, these results are quite preliminary yet, but basically we want to demonstrate that we can avoid the use of global scaling factors that are actually nowadays used during collision analysis. And we want to show that without covariance correction, it is no longer needed to do that post-processing of the analysis in the collision. But also we have seen that the probability of collision evolution is much better without covariance, because for a high risk event, we are able to detect the event almost 3 days earlier than the typical covariance that we have operationally. And well, just now to finish, regarding the future work, the first thing that we were planning to do is to extend the initial part of the methodology not to a single object, but to a whole catalog. And instead of investigating the same object during a very long time span, we want to focus on a short time span, but with a lot of objects, to get uncertainty estimates that are able to help us with the cataloging process and that are applicable to a whole catalog. And then afterwards, we will start tackling the determination of stochastic correlation parameters in the orbital regimes. Well, that's basically all. Thank you for your attention. And if you have any further questions, let me know.